Good morning. Today we are going to start the new lesson, strain energy. Okay, very easy lesson, and today and tomorrow we are going to finish this in 2 hours. But today, very few students have joined the lectures. So far, only 39 or 40 students have joined. Please let me know if you have any difficulty so that I can make the necessary changes. Okay. Strain energy. Okay. Uh, Now, what is the strain energy? If you consider any material, any metal, okay, if it is subjected to the axial load, suppose it is subjected to the axial load P. Here, this initial length is L, and the cross-sectional area is A. A is the cross-sectional area. Now, because of this axial force applied, here this material will get elongated. The elongation of the material because of this load is delta L, that you know. Now, because of this elongation of the material, here there is a displacement of this load through this distance delta L. Okay, this is the force and this is the displacement or the distance traveled by that load. Okay, so when we apply the load P, here there is a displacement of that load, and we know that when a force is applied and if there is a displacement in the direction of the applied force, the work is done. Okay, so in this case, here the work done by this force here is equal to P into displacement in the direction of that force, that is P into delta L is the work done. But we know that the work done is the energy. Work done is the one kind of energy. And energy cannot be created and not destroyed as per the law of conservation of energy. Okay, so work done is the energy and energy cannot be created or destroyed. Here, so this work which is done by this applied force P, here what happened with that load or what happened with that energy? Okay, here, so this energy, that is the work done by this load, here this energy is stored in the material here because of the deformation. Here that energy is stored in the material. Here, so this energy which is stored in the material because of the deformation here is known as the strain energy. Okay, here, so how can we define the strain energy or exactly strain energy hai kya? Here, so it is the energy stored in the material because of some deformation is known as the strain energy. Okay, it is one kind of potential energy only. Here, because it is stored inside the material, so we can say that it is the potential energy. Clear? But if anybody asks you here what is the strain energy, here, so strain energy is the energy stored in the material because of its deformation, because of its straining. Here, that's why it is known as a strain energy. Here, and in equilibrium, very important thing, in equilibrium, here the strain energy which is denoted by U here is equal to the work done by this external applied force. Yeah, the strain energy is equal to the work done by this external applied force. Now, in this lesson, we have to find out the strain energy stored in the different component because of the different type of loading. Yeah. So, the first thing which we have to study is the strain energy stored due to the axial load. Strain energy stored due to the axial load. Okay. Here, in this axial load also, here we are going to consider the different, this is the axial load. Here in axial load also we are going to consider the different type of loading here, and because of that loading here how much amount of strain energy is stored, that we are going to calculate here. So remember, basic concept of strain energy is equal to the work done here, and it is one kind of energy. Okay, here the work done is converted into strain energy. So the strain energy is stored in the component because of the axial load we have to study, and in axial load also we are going to consider the three different cases. The first one, when the axial load is a gradually applied load. Here when the load applied is gradually. Okay, we have studied on the UTM how the load is applied gradually. The gradually applied load means the magnitude of the load here is increased gradually. Here with respect to time, with respect to this elongation, here we are slowly increasing the magnitude of that load. So that load is known as a gradually applied load. Here on UTM, we are applying the load gradually. Here we are increasing the magnitude of that load very slowly. Here, so that load is known as a gradually applied load. Here, and for all our calculation till now, unless and until it is mentioned, here we are assume that the applied load is a gradually applied load. Okay. The second type of load which we are going to consider here for axial load only, but the second type of load is a suddenly applied load. We are suddenly applied load. Okay. Now, what happens in the suddenly applied load? The load applied is all of sudden. Okay. Here, for example, when we sit on the chair or when we sit on the bench, here our weight is applied on that bench or on that chair suddenly. Okay. Here we are not sitting gradually. Here 1 Newton, 2 Newton, 10 Newton, 20 Newton, not like that. Here our entire weight is applied all of suddenly, so that is known as a sudden applied load. Here, for example, if this is certain load, if I place this load here on this surface from very small distance here and I release it here, so this load applied on this surface is suddenly. That is known as a sudden applied load. Here, I hope that you understand the difference between the gradually applied load and the suddenly applied load. Here, in axial load, the third type of load which we are going to study is the impact load. When the load applied with some momentum. Here, before that, we have studied the impact testing machine. Here, we have conducted any doubt? Don't unmute unnecessarily. Okay. The third axial type of load which we are going to study is the impact load. Here, before this, we have studied the impact testing machine. Here, we have conducted the experiment also. Here, ISOD and impact testing machine. So, in that case, here the load applied on the specimen is the impact load. Here, so what happened in that machine? Here, a very large amount of mass. Here, we have released from certain height. Yes, when it is at certain height, it is having the potential energy. Here, and when we release it, that potential energy gets converted into kinetic energy, and with that kinetic energy, it collides on that specimen. Here, so this load is known as the impact load. The very best example of the impact load is the hammer blow. Here, hammer blow is the impact load. When we hammer something with the help of hammer, here then that is known as the impact load. Here, so don't get confused between the sudden applied load and the impact load. Here, in sudden applied load, the load is applied all of suddenly without any velocity or without any momentum. Okay, whereas in impact load, the load applied with some momentum. Here, when we hammer something, here, when we hammer something, then that hammer is having some mass here, and we drop it with some velocity. Understood? Here means it is having some momentum. So when the load applied with some momentum, here then it is known as the impact load. Understood? Here when you punch somebody, here then that is also the impact load. Here because it is having some momentum, it is having some velocity. Here, so that load is known as the impact load. So initially or today, here we are going to study the strain energy stored because of the axial load, and in axial load we are going to consider the three type of load: gradually applied load, sudden applied load, and the impact load. Here the next part is the strain energy stored because of the bending. Okay, so if I consider suppose the simply supported beam here, and if such type of load is applied here, because of this load the beam will get bent. Here there is a bending moment, and because of the bending moment the beam will get deflect. Here it will get bent, and because of that here there is work done and the strain energy is stored in the material. So we have to study the strain energy stored because of the bending here. And third one is the strain energy stored because of the twisting, or strain energy stored due to the torsion here because of the twisting moment. Okay, so this is the syllabus here which we have to cover in this lesson, strain energy. Okay, so let's find out how much amount of strain energy is stored in the material because of the gradual applied load. Yeah, and basic concept is the strain energy is equal to the work done. Yeah, so the first one is the strain energy stored because of the gradually applied load. Yeah, under axial loading. Okay, so first one is the strain energy due to gradually applied load. Okay, let's consider this is one specimen whose cross-sectional area is A, length is L, okay, and at one end it is fixed, yeah, and at other end I'm applying a force P, which is a gradually applied load. Because of this force P, there is a one axial reactive force here also, but I consider that it is fixed, yeah. Now, when I apply the load P gradually, yeah, this material will get deformed. Let the deformation of this material is delta L. Okay, here. Now, if I plot the graph of this gradually applied load versus deformation, here I am drawing the graph. Here it is the graph of here gradually applied load versus the deformation. Here, so this P is the force and delta L is the deformation. Yeah. Now here, when the P is 0, the deformation is 0, and the load increases gradually, and so according to the load, there is a deformation. Here means, so if I plot the graph of P versus delta L, it is a linear graph. Okay, so this is the P versus delta L graph. Here, so when the force P is there, the deformation is delta L. Here, now whenever we plot the graph of force versus deformation, here, remember this thing, the area under this graph here gives you the work done. So, yeah, actually, work done is equal to the force into delta L. That all of you know. Here, when a force is applied on the object, here, and because of this, here, suppose the displacement of this object is ds, then here the work done is equal to P into ds. But remember, we can directly write P into ds provided here for this much displacement, the P is constant. Then we can write directly P into ds. If the P is remain constant, then only we can write down P into ds. Here, if that during this displacement, if the P varies, here, then we have to consider a very small displacement ds. Here, this is the initial displacement S1 and final displacement S2. Here, and during this S1 to S2, here the force P varies. If the P force varies, here, then how we can calculate the work done? Then in that case, we can't write P into this S. Work done can be written as P into S. S is the displacement, which is S2 minus S1. So here, if the P varies, we can't write the work done P into S. Then how we can calculate the work done in that case? If the force varies, then if the force varies, then the work done is equal to, we are assuming that for the small displacement, the force is constant. So work done for the small displacement is P into ds, and where this displacement varies from limit S1 to S2. So you have to integrate it from limit S1 to S2. So this gives you the work done by the force if the force varies. Here, this is the basic concept. Here you must be knowing that. Here, so in this case, so here also, even in this case also, if the force P varies, if I plot the graph of force P versus displacement, here then the area under that curve gives you the work done. So here also, since the force applied is gradually, here because of the gradually applied load, here there is a deformation delta L. Okay, and during this deformation or during this displacement, the force P is not constant. It varies because it is a gradually applied load. Okay, and if I plot the graph, then the area under this graph gives you the work done. Okay, so we know that now because of this we have to calculate how much is the strain energy. Now we know that the strain energy stored, strain energy is denoted by U. Here the strain energy stored equal to the work done. It is equal to the work done. And when the load applied is gradually, and because of that, if the deformation is delta L, here then this work done is equal to the area under this graph, which is equal to half into delta L or P into delta L. Not only P into delta L, but it is half into P into delta L. Here it is the area under this graph. Here this is the work done. Here which is equal to the strain energy stored in the material. Now we know that here this P is the applied load, and because of this, and it is a gradually applied load. Because of that, some stress is induced in the material. Clear? So the relation between that applied force and the stress, clear, can be written as stress into area. P can be written as stress into area. This is the stress induced in the material because of this gradually applied load. Here into this delta L because of the gradually applied load. Here we know that the delta L equal to PL upon AE, which can, this P upon A is the stress because of this gradually applied load. So it is sigma into L upon E. So here if I substitute that sigma L upon E, yeah, so I will get the strain energy stored because of the gradually applied load is equal to, it is sigma square into A into L upon E. A is the cross-sectional area and L is the length. Here means A into L is the volume if the rod is having the uniform area. Where we are considering it here that the rod is having the uniform area, the strain energy stored by the taper rod is different. Okay, here this formula is not applicable for this taper rod. Here, so strain energy stored for the gradually applied load U equal to sigma square AL upon E. I am writing the formula here so that you can refer that formula while solving the sum. And I already posted that PDF file here for the formulas and question bank here on your WhatsApp group. Okay, so the first important thing is the strain energy equal to the work done. Then for gradually applied load, the strain energy can be written as, this is the first, I am not writing it here, it is a gradually applied load. Here this U equal to sigma square AL upon 2E. Here where for gradually applied load this sigma equal to P upon A. Here this is for gradually applied load. Okay. Now for gradually applied load, here this delta L, here you can write it in terms of PL upon AE, what we have studied in the first lesson. Here or can be written in terms of stress. So it is sigma L upon E. This is the stress, this is the deformation, and this is the strain energy because of the gradually applied load. Here the second one is the strain energy stored due to the sudden applied load. Okay. Before that, here I would like to tell you one thing. If you observe this formula, strain energy equal to sigma square L upon E. Here from this one I can write down the strain energy upon A into L, here which is equal to sigma square upon E. Okay. So this U upon L, AL, here this is the strain energy stored per unit volume. Here the cross-sectional area is A and the length is L, so it becomes the volume. So strain energy per unit volume here is known as the resilience. It is known as resilience. Here, so resilience is what? It is the strain energy. How can you define the resilience? It is the strain energy stored per unit volume here, which is equal to sigma square upon E. Okay. Now we'll observe that here the strain energy is proportional to the stress. Okay. If the stress value increases, the amount of strain energy stored is also increases. Here, so the strain energy stored in the material here at elastic limit. Here at elastic limit, this is the elastic limit. So corresponding to this stress value, here the strain energy is stored in the material here is known as a proof resilience, which is the maximum strain energy stored here at elastic limit. This is known as a proof resilience. It is the strain energy stored in the material here per unit volume at elastic limit. Okay, here that is known as a proof resilience, and proof resilience is the mechanical property of the material. Okay, here with help of that proof resilience, we'll come to know that the ability of the material to withstand the shocks. Okay, here that is known as a proof resilience. Okay, so is that clear? What is strain energy, what is resilience, and what is the proof resilience? Here, so proof resilience is the mechanical property of the material. Here, with the help of which we'll come to know that here the amount of shocks the material can withstand. Okay, here that is the proof resilience. Okay, this resilience is the strain energy stored per unit volume here, which is equal to sigma square upon 2E. Okay, now the next one is the strain energy due to the sudden applied load. Second one is the strain energy stored due to the sudden applied load. Strain energy due to sudden applied load. Let's consider the same slender rod of cross-sectional area is A and length is L. Now the axial applied load, here the load applied is axially only. Here, but this applied load is the sudden applied load. The entire magnitude of P is applied suddenly. Here, so it is known as a sudden applied load. Now, because of this sudden applied load, let the deformation of this material is delta L suffix S. Okay, the value of deformation because of the, suppose if I apply the load of 100 kilonewton. Now, if I apply the 100 kilonewton load, gradually the deformation will be different. Whereas if I apply the 100 kilonewton load, suddenly the deformation will be different. Here, for sudden applied load, we cannot use this PL upon AE formula. Okay, PL upon AE formula we cannot use for the sudden applied load to calculate the deformation. That's why because of this sudden applied load, ये जो deformation है, I've denoted it as delta L suffix F. Okay, this is the deformation because of the sudden applied load. Yeah. Now in this case, here the work done by the load, or if I plot the graph of P versus delta L. Yeah. So for this, when deformation is delta L, corresponding to this, the force is P, and the force P is remain constant because it is a sudden applied load. Here, throughout this deformation, the magnitude of the force P is constant. Here, so the force P is constant. So this is the area under the P versus deformation graph for the sudden applied load. Here, now we know that the work done, strain energy stored equal to the work done. Here, now the strain energy stored here is equal to, from this equation, it is sigma square AL upon 2E. The same formula can be written over here, only the stress here is the stress induced because of the sudden applied load. Here, जैसे delta L का explain किया मैंने, at the similar way, the stress will also not be same here for the gradually applied load and the sudden applied load. Here, stress का value change हो जाएगा. Understood? Here, so if corresponding to this sudden applied load, if the stress induces sigma suffix S, here, then the strain energy stored is equal to sigma S square into area into L upon 2E. It is not the gradually applied load. It is the sudden applied load, so I am denoting it sigma S here, which is equal to the work done. Okay. Now, how much the work done in this case? It is P into delta LS equal to the area under this graph. It is P into delta LS. Last time the work done was half P into delta L. Now it is P into delta LS. That's why I'm writing that delta LS. Okay. Now if I equate this, yeah. Now this is the P is the gradually applied load. Okay, and this is the strain energy stored here because of the sudden applied load. Here this P is the sudden applied load, and this is the work done. So it is this can be written as, this P can be written as, it is sigma S into area. Here this is a sudden applied load, so the stress induced is the sudden stresses because of the sudden applied load. Okay, it is not the stress induced because of the gradual applied load. Here into delta LS. Just 1 minute. We have to get the relation between the delta sigma S and the P here. So I will not express this P in terms of sigma S, let it in terms of P only, and this delta LS I will write in terms of stress here. So it is sigma S into L upon E. Okay, this is the stress induced because of the sudden applied load. Here, so it is sigma S into L upon E. Here, which is equal to sigma S square AL upon 2E. Sigma S square AL upon 2E equal to this P into delta LS equal to sigma S upon L, sigma S L upon E. So this E get cancelled, one sigma S get cancelled, one L get cancelled. Here, so we will get this P equal to, or stress sigma S equal to 2P upon A. Okay, if the same load applied gradually, if the force P is applied gradually, the stress because of the corresponding stress because of the gradually applied load is P upon A. Okay, here, but when the force applied is sudden applied load, here the stress induced is equal to, it is 2P upon A. Here from this one thing I would like to conclude is that here if the same load is applied gradually, here then the stress induced is half of the stress induced because of the sudden applied load, or the stress induced because of the sudden applied load is twice than the load applied gradually, or the stress induced because of the gradually applied load. Here the amount of load is same, but the stresses are different even though the cross sectional area is same. Here this happened because of the gradually applied load and the sudden applied load. Here, so for sudden applied load, the stress is equal to 2P upon A. For gradual applied load, the stress equal to P upon A. Okay, and the strain energy stored here because of the sudden applied load. Here you can use the same formula, only sigma S equal to 2P upon A. Here, so the strain energy you can use the same formula, it is sigma square AL upon 2E. But this sigma is the sigma S. Here stress induced because of the sudden applied load, and the stress induced because of sudden applied load equal to 2P upon A. Here again, in this case, here this delta LS, here don't use the formula when sudden applied load, and if you want to calculate the deformation, here don't use the formula PL upon AE. Okay, instead of that, here you use this formula. Here calculate the stress induced because of the sudden applied load. Here, and with help of that you can calculate the deformation, which is equal to sigma S into L upon E. Okay, here this is the strain energy stored in the material because of the sudden applied load. Okay, here I have not expressed this P in terms of the stress because I want to get the relation between the stress because of the sudden applied load and the force P, which is the sudden applied load. Okay, any doubt? Here unmute yourself and ask if you have any doubt. Listen, what I am observing, only somewhat 57, 58 students are there. Why such less attendance is there? All of you write your name and roll number in the chat box. Here in next 5 minutes you have to write the name and roll number in the chat box. Here I am observing that only 54 and few more. 1, 2, 3, 4, 5. Means at the most 58, 59 students are there. I will cross check. The next one is the strain energy stored due to the impact load. Strain energy stored due to the impact loading. Impact loading means when the load is applied from certain height. Here, when I drop the load from certain height, here then because of that height, here it will gain some velocity and it will apply with some velocity. That is known as a sudden applied load. Here, let's consider we have to find out the strain energy stored in this rod whose diameter is, whose cross-sectional area is A and the length is L. Let this length is L and the cross-sectional area is A. Okay. Now at the end of this rod, here there is one small thin rigid collar is there. Here this is a collar. Here, this collar we are providing just to stop the load apply. Okay, here now I am going to apply the load W. Suppose this is the load W. Here in the form of one collar, this is the load W. Here we are dropping from the certain height here on this collar, and because of this collar, here its momentum is suddenly stopped. Here its velocity suddenly stopped and momentum becomes zero. Here, and let this weight W, this is the weight W, let this weight W is dropped here from the height h. Because of this collar, it will not move further. Okay, here this collar is used only for that. Here, so L is the length of that rod, h is the height from where the load is dropped, height of the load. Here, remember, now while solving the sum, you have just recall this figure. Here, because while solving the sum, I am not going to draw the figure. Here, the L is the length, A is the cross-sectional area, h is the height from where the weight is dropped. Here, and because of this, here the deformation is delta L. You can write here the delta Li, deformation because of the impact loading. Here, and this deformation is also something different than this. Here, when the impact load is there, the stress induced is also different. Okay, here you cannot use this formula, neither this formula you can use to calculate the stress because of the impact loading. Here, instead of W, you can see it as a P also. Here, one and the same thing. Here, instead of W, I can consider it as a P. So, I am applying the load of P Newton. Here, but the P Newton load is applied suddenly. Here, sorry, impact load, in the form of impact load. Here, because I dropped it from the height of h meter. Here, so P is the external applied load. Here, it is applied in, with some momentum. That's why it becomes the impact loading, and I drop it from the height h. Here, because of that, the deformation is delta Li. Okay, now from this, when the same load P is applied gradually, the stress is sigma square Al upon 2E. Okay, now for the impact loading, here the strain energy can be written as sigma I square into Al upon 2E. Here same formula I can use, but only the stress is sigma I, stress because of the impact loading. Okay, here this is the strain energy. Now we know that the strain energy is equal to the work done. Here strain energy equal to the work done. Now in this case, how much is the work done? Here the load applied is P, and it is drop on this material from the height of h, and after that impact, here the material gets deformed through delta Li. Means the total displacement of the load from initial position to the final position here is h plus delta Li. So work done equal to P into, in bracket, it is h plus delta Li. It is a deformation because of the impact loading. Okay, here, and this is equal to the stress, strain energy. Here, so I can write P into h plus delta Li. This is the work done, which is equal to the strain energy sigma square Al upon 2E. Okay, here P into h plus delta Li equal to sigma I square Al upon 2E. Here have you understood this? Okay. Then this P into h plus delta Li can be written in terms of corresponding stress. Here, so it is sigma I into L upon E. Here, which is equal to sigma I square Al upon 2E. Okay. Now, if I simplify this, okay, if I simplify this, here it is P H plus P L upon E into sigma I minus, I will take it on this side, it is sigma I square into A into L upon 2E equal to 0. If I rearrange it here, and if you observe it carefully, you will observe that this is a quadratic equation in sigma I. It is a quadratic equation in sigma I, which is the stress induced because of the impact load. Yeah, And if I solve this by our normal formula, here it is minus b plus it is minus b plus minus under root of b square minus 4ac upon 2a. If I use this formula and if I simplify this here, you will get the corresponding stress induced in the material because of the impact loading. Okay, and you will get the formula here, the stress induced because of impact load. Now I am not going to simplify this. Here you have to simplify this. This is a quadratic equation in sigma I. If you solve this here, you will get the stress induced because of the impact loading. Okay, and what is the stress induced because of the impact loading? Here, if you simplify this, here the formula is, it is P upon A plus, in bracket, here it is P upon A whole square plus here 2 PEH upon AL. Okay, this formula you will get here, or if I take P upon A common, here then it is 1 plus, sorry, this is in under root. Okay, this is in under root. This bracket is in under root here. So P upon A plus under root of P by A whole square plus 2 PEH upon AL. Here, this formula will get after simplifying this quadratic equation. Okay. Then if I take P upon A common, here then in bracket, P upon A in bracket 1 plus under root of 1 plus, now here it is under root of P upon A, but I have taken common under root of, outside the under root of P upon A. So it will be 1 plus under root of 1 plus 2 EH upon PL. Okay, because if I take it inside, it becomes P square upon A square. So 1 P get cancelled. Okay, and you will get it A over here. 2 A 1 A बाकी रहेगा, A स्क्वायर अगर लिया तो एक ये इधर आएगा 2AEH upon PL, 2AEH upon PL. Okay, now it is correct. Now if I take, let's check whether we are getting this term or not. If I take it inside, so then this 2AEH upon PL into inside, it will become P square upon A square. Okay, so 1A get cancelled, 1P get cancelled. Yeah, so it is 2PEH upon this A and this L. Yeah, so you will get this term. Okay, so either you remember this formula or this formula. This is a stress induced because of the impact loading. Here concept is very simple. Here we have find out the work done. Here we are equated with the strain energy. The strain energy basic formula is sigma square AL upon 2E. But since we are considering it as the impact loading, so corresponding stress you have to consider it as a sigma I here, and if you simplify this, we'll get this formula here. So I'm writing it here. The third formula is the stress induced because of the impact load. Okay, so which is equal to, it is P upon A into, in bracket, sorry, plus in bracket under root of P by A whole square, P by A whole square plus 2PEH upon AL. Or if I take P upon A common, then it is P upon A into, in bracket, 1 plus under root of 1 plus 2 AEH upon PL. Okay, this is the formula, and once you get the stress because of the impact loading, then the strain energy stored equal to sigma I square AL upon 2E, and this deformation delta Li because of that impact loading here can be written as delta Li equal to sigma I into L upon E. Same formula. Listen, this strain energy and delta L formula is same. Now in strain energy, I suggest if it is asked to calculate the deformation because of the impact loading or because of the sudden applied load, don't use the formula PL upon E, even though it is axial load. Okay, instead of that corresponding to the load, given load, first calculate the stress and use that stress to calculate the deformation as well as the strain energy. Here, this basic formula only you have to remember. Here, only the formula of the stresses will change. Here, any doubt? Any doubt? I will solve few questions here which are given to you in the question bank. Now it is, listen, if you know this concept here, you can use it directly. Okay. Direct put the value and get the answer. Write down the given data. Here just you have to remember this concept. You have to write it, you have to keep it in your mind. No need to draw the figure, just write down the given data and solve the sum. Okay. The sum number 2, I will explain. You have to solve it at your home. Sum number 2. At least we have to finish the 2 sums. Sum number 2. A solid vertical prismatic bar of equilateral triangular section of size 30 mm is firmly fixed at a top A. Listen to me. Solid vertical prismatic rod is fixed at top. Here, and the cross section is a triangular one. Here, its cross section is triangular one. It is a equilateral triangle of side 30 mm. From this one, you can calculate the area. Area is not given directly here, but with the help of that cross-sectional area, you can calculate the area. Is firmly fixed at the top. A rigid collar at a distance of 800 mm from the top. Here, there is one rigid collar at the bottom at a distance of 800 mm from the top. It means that the length of the rod, which is under consideration, is 800 mm, L equal to 800 mm. Calculate the strain energy stored in each of the following cases. Here, when a pull of 15 kN is applied. Here, when a force P is applied is 15 kN, that is 15 into 10 to 3 Newton. Okay, one thing I forgot to tell you here, that strain energy is the energy whose unit will be joule. Okay. Here, so joule is nothing but a Newton meter. Newton meter is the joule. So here, if you use millimeter and Newton, so initially you will get the answer in Newton millimeter. Then convert it into Newton meter and write it as a joule. Here, जो पहले आंसर आएगा Newton millimeter को directly joule मत लिखो. Okay. Here, so this force P applied is 15 into 10 to 3 Newton. This much force is applied. Okay. Now, when this force is applied, here you have to calculate the strain energy in this rod when the force is applied gradually. Second, when the force applied is suddenly. And third, when the force is the impact. When the applied force is the impact force. Here, so in these 3 cases, you have to calculate the strain energy stored. Okay. Now, just you have to substitute the value and get the answer. You have to substitute the value and get the answer. Okay. Here, for finding the strain energy stored due to the gradually applied load, here everything is given, area is given, L is given, force P applied is given. Here the modulus of elasticity is also given for the material. Here let's take E equal to 200 into 10 raised to 3 MPa. Here that is 2 into 10 raised to 5 MPa, Newton per millimeter square. E value is given. Here the one by one for gradually applied load. Strain energy for the gradually applied load. Here the strain energy is equal to sigma square AL upon 2E. Okay. Here then for suddenly applied load. For suddenly, the strain energy equal to sigma S square AL upon 2E, same formula. And for impact load, the strain energy equal to sigma I square AL upon 2E. Everything is same. Only the value of stress is varying. Here sigma equal to P upon A. Here sigma S equal to 2P upon A. And here sigma I equal to, the formula is P upon A plus, in brackets, under root of this formula you write down. Substitute the value, you will get the stress first. Substitute that value of stress in this formula, you will get the strain energy. Initially, you will get the strain energy in the form of Newton millimeter, and then convert it into Newton meter and write it as a joule. Okay. So sometimes it is asked to calculate the delta L. If it is asked to calculate the delta L for gradually applied load, it is sigma L upon E. For suddenly applied load also, this delta L equal to sigma S L upon E. And for impact load, it is delta L equal to sigma I into L upon E. Okay, in this way we can calculate the deformation. Now sometimes this deformation would have been given and it is asked to calculate the load. Okay, it is asked to calculate this distance h. Understood? Here or load. Here some different, but basic things is same. Okay. Now the second sum is the sum number 5. This you have to solve at your home. Very simple. Just put the value and get the answer if you understood this theory. Sum number 5. What is given? A wagon weighing 35 kilonewton. Here a railway wagon is there whose weight is 35 kilonewton is attached to a wire rope. Okay. And moving down an incline at a speed of 3.6 kilometer per hour. It is moving with a uniform speed of 3.6 kilometer per hour. Then the rope jumps and wagon is suddenly brought to rest. If the length of the rope is 60 meter, at the time suddenly stoppage, calculate the maximum instantaneous stress and maximum instantaneous elongation produced. The diameter of the rope is 40 millimeter. Okay, here what is given? A wagon is moving on a wagon weighing 35 kilograms is attached to a wire rope and moving down on an incline. Here the wagon is moving down on this incline. Here how much is the inclination angle? It is also not given. Okay, this wagon is moving down. Here and one wire is connected to this wagon and one end of the wire is fixed to some support, rigid support. Here initially this wire is loose. Here and this wagon is moving with a speed of 3.6 kilometer per hour. Here means the velocity of this wagon is 3.6 into 5 by 18. How much? 10 meter per second. Calculate. It is yes, 3.6 kilometer per hour. Yes, so 3.6 into 5 by 18. Calculate and tell me the answer. Is it 10 meter per second?
Sir, it is 1 meter per second.
तो इतना टाइम क्यों लगता है? बाकी लोग सो रहे क्या? या प्रवचन सुन रहे बाकी लोग? अनम्यूट करके बोलते नहीं आता है आप लोगों को? अभी टाइप कर रहे, सर ने बोला 10 मीटर पर सेकंड, तो बस सुन रहे प्रवचन। ऑनलाइन है इसका मतलब ये नहीं है कि वीडियो लगा देने का और सोने का। Here I will not share from next time, from today I am not going to share any video lecture on your classroom. Okay, you have to be present here only during the class. It is 1 meter per second. This is the velocity of that wagon. It is moving with a uniform velocity. Here and when this wagon at certain position of the wagon, here this rope becomes straight. Here means there is it has certain length. Here after that much length, here because of this tension in the rope, that wagon come to rest. Here the wagon come to rest. Yeah. So because of this loading, here there is a sudden load or impact load, you can say. There is an impact load on this wire. Here this is the wire or this is the rope. Here it is asked, because of this sudden stoppage, here how much is the deformation of the road and how much is the instantaneous stress induced in that rope, that you have to calculate. Okay. Now first unmute yourself and tell me, here when this wagon is suddenly come to rest, here which type of load is acting on this rope? Is it the impact load? Is it the sudden applied load, or is it the gradually applied load? Here just imagine and tell me, here rope पे जो load apply होगा because of the sudden stoppage of this wagon, is it the sudden applied load or the impact load? Gradually applied load तो है ही नहीं है. Here,
Suddenly applied.
Listen, here I told you that sudden applied load क्या होता है? Here in sudden applied load, here the load applied all of suddenly without any velocity. Okay, but in impact load, here the load applied with some velocity. So here this wagon is in some velocity and that velocity is suddenly stopped. Okay, so it is similar to the impact load and not a sudden applied load. Okay, it is similar to the impact load. It is not a sudden applied load. Okay, now how we can calculate if it is the impact load? How to calculate all this strain energy? Even if it is asked the strain energy, then how to calculate this stress here and how to calculate this deformation. Here, if I know the stress, I can calculate the deformation. But how to calculate the stress? Here it is P upon A and all this factor is there, H is there. Here length of the rope is given. Here how much is the length of the rope? The weight of the wagon is P equal to the load weight of the wagon is 35 kilonewton or 35 into 10 to 3 Newton. Its weight is known to you. But listen, this is the gradually, these formulas which we are derived, these are for the axial load. Yes, so actual axial load acting on the this rope here is the component of this weight acting vertically downward. Yes, so actually this component is applied on this rope. So P is given, but for that you require the angle theta, but angle theta is not given. Okay. So this is the load or the weight of the wagon. The velocity is 1 meter per second. When the rope jumps and wagon is suddenly brought to rest, if the length of the rope is 60 meter, when the wagon comes to rest, the length of the rope is 60 meter, which is equal to 60 into 10 to 3 millimeter. Calculate the maximum instantaneous stress and maximum instantaneous elongation produced. Diameter of the rope is 40 millimeter. Diameter is given as 40 millimeter. From this one, you can calculate the cross-sectional area pi by 4 into d square. You will get the area in millimeter square. Here, area of this rope in which you have to calculate the strain energy and the delta L and sigma. Here, E is equal to 2.1 into 10 to 5 Newton per millimeter square. Tell me how to calculate this. Here, basic concept is required to solve this sum. Basic concept. Listen, when this rope is connected to the wagon, okay, when this wagon comes to rest, at that instant, the velocity of the wagon was 1 meter per second. When it comes to rest here, and it is having some weight, or means it is having some mass here, means when it comes to rest at that instant, here it possesses some kinetic energy. Here how much is the kinetic energy of the wagon? It is half mv square when it comes to rest suddenly. This was the kinetic energy. Here means the kinetic energy comes to rest, comes to 0 from this value. It is half into 35 into 10 raised to 3 upon 9.81, ये mass हो गया into 1 square. This was the kinetic energy just before come to rest. Here and final kinetic energy after rest, after stopping that wagon, here it becomes 0. Here, so there is a loss of kinetic energy. There is a loss of energy. तो ये जो energy था, जो loss हो गया, वो गया कहाँ पे?
In the rope.
In the rope. It's stored in the rope in the form of strain energy. Okay, so ये जो kinetic energy है, here which lost, here this kinetic energy is stored in the rope in the form of strain energy. Yeah. So earlier when we discussed the theory, at that time I told you that the strain energy is equal to the work done. That was the case for that. Here, because here the work done is not there, but another form of energy is there, which is the kinetic energy. So that kinetic energy loss is there. So that kinetic energy is stored in the rope. Here, so the strain energy is stored in the rope. Strain energy stored in the rope is equal to the kinetic energy of wagon. And how much is the kinetic energy of wagon? It is half into 35 into 10 to the cube upon 9.81. This is the mass into square of the velocity. This is the strain energy in the rope. Okay, here this value is in the joule. This is in Newton millimeter. Sorry, Newton meter. This is in the joule. When the mass is in the kg and velocity is in meter per second, here the kinetic energy in the joule. It is in the Newton meter. Okay, so from this one you can get the strain energy stored in the rope. Understood? And once you get the strain energy here, so the strain energy stored here is equal to sigma I square AL upon 2E. Use this formula, ये strain energy हो गया. Here, so if you substitute that strain energy here, area is known to you, length is known to you, E is known to you. Here, this strain energy is also known to you. Substitute that, from this one you will get the sigma I. This is the instantaneous stress induced in the rope. Okay, just put the proper units, convert the units properly. Here, and once you get the instantaneous stress, here then the instantaneous deformation here can be written as sigma I into L upon E. Everything is known to you. Substitute that, you will get the instantaneous deformation of the rope. Here, so here in this sum, the strain energy stored in the rope is equal to the kinetic energy of the wagon. Here, this is the basic concept. Everything is same. Remaining part is same. Here, any doubt? Any doubt? I hope that all of you have entered your name and the roll number. Okay, this is the end of the today's lecture. Here tomorrow we'll continue the second part of this. Okay, listen, I'm not those who are writing the name and roll number now. Here I already declared. Here the roll number and name should not be more than 60. Here I'll consider the first 60 students only for the attendance. Thank you.